Okay, so this will be the last hypothesis test that we do for the term. There are plenty of others, but we have to stop somewhere. This one is for comparing two unknown population means. Right, so we've done comparing two unknown population proportions. Now we do means. Right? So the proportions are for categorical variables, means are for quantitative variables. So this will be one for quantitative variables. And the idea is typically that there are two populations we're interested in and we think that they are different in some way. So structuring the test exactly like we do all the others, we temporarily assume there's no difference in the two populations so that they have the same population means. We collect samples, random samples from both populations, find the sample means in the two samples, compare them, and then see if there's enough of a difference in the two sample means to cast doubt on our assumption that there's no difference in the two population means. All right, so the mechanics of the test work a little bit differently from the ones we've done before. When you have two samples, there's more to keep track of, more variables, so it can be a little tricky to keep it all straight. But if we do so, then the structure, the logic, all of that is identical. There's just a little difference in the calculation. So get past that, they all look the same. So if there's really no difference, you find the test statistic, and then using the test statistic, you find the p-value to see how rare that test statistic is if the assumption of no difference is true. And then based on how rare the result is, you either reject the null if it's too rare to be plausibly attributed to chance, or you fail to reject the null, in which case you're not accepting it necessarily, you're just saying you don't have enough evidence yet to reject it. Okay, so the two means test. It's a little bit of a silly example, I guess, but we have two college students arguing over whether or not Samford students or BSc students are smarter. And the way they've decided to test this is by sampling students from both institutions and calculating the mean IQs in the sample. All right, so the Samford students from Samford, 60 are chosen at random. The mean IQ in that sample is 102, and the standard deviation of the sample is 13. And then for the BSc students, 30 are sampled randomly with a mean IQ of 110 and a standard deviation of 10. And our predetermined significance level is 0.01, so our p-value needs to be less than that. We have to have a less than 1% chance of getting our data if there's really no difference in order to reject the null. Our null hypothesis is that there's no difference, that we're saying here that the overall mean IQ for all the Samford students and all the BSc students is the same. All right, our alternative, since the students are arguing, right, one thinks it goes one way, one thinks it goes the other, so we're going to stick with it not equal to for the alternative assumption. We're just looking for a difference. That makes it a two-tailed test. And remember, that affects the p-value later on when you have to take one of either the left or right area and double it. All right, our requirements to run a test and get useful results is that the samples are chosen randomly. That is stated, at least for the Samford students, in the example. So it's applied for the BSc students as well. The samples have to be independent. That checks out because who we select from Samford has no influence on who we select from BSc. And then we have to have at least 30 in each of the samples, and that's okay here too. We have exactly 30 for BSc, 60 for Samford. So the rest of this is plugging in lots of numbers, keeping them straight and not messing up on the calculator. All right, so our test statistic, because we have unknown population standard deviations and are using S's, sample standard deviations, that brings into play t-distributions for our statistic. So just like for an unknown population mean with unknown sigma, we use a t-distribution. We do that here as well. Now, calculating the degrees of freedom, there's just like one extra step. In the one sample case, it's just the sample size minus 1. In the two sample case, we're taking sample size minus 1, but since we have two different sample sizes, we're conservative and we pick the smaller of the 2 degrees of freedom. Right? So sample size minus 1 for both samples and then pick the smaller of the 2. So our degrees of freedom in this case will be 29. 30 minus 1 is 29, 60 minus 1 is 59, 29 is smaller. All right, so we plug in everything we know. Sample mean for Samford, sample mean for BSC, sample standard deviation for Samford squared, so 13 squared is 169, that's already been done. Sample standard deviation for BSC is 10, squared is 100, so that's been done as well. And then the two sample sizes, 60 and 30, respectively. That gives us a standard error of 2.48, and we're dividing that into minus 8, so our t statistic is this minus 3.226. Because we're doing a two-tailed test, we would have to find the area under the appropriate t-distribution. So this would be the t-distribution with 29 degrees of freedom. We find the area under that one to the left of minus 3.226 and to the right of 3.226 and add them together. Or we take advantage of the symmetry there, find one of them and multiply it by 2. All right, so this is one where you have to use technology of some kind because we don't have an empirical rule for t-distributions. So I take twice the probability of a t-distribution with 29 degrees of freedom being less than or equal to minus 3.226. That's a job for StatCrunch, which we can take a look at in a separate video, but the result is a 0.0019 for the overall p-value. Well, that p-value is less than 0.01, the predetermined significance level. So we would conclude that our two samples provide enough evidence of a difference in the IQs that we would reject the assumption that there wasn't a difference. Right? So reject the null hypothesis in favor of concluding that there is a difference, and in fact, based on our samples, the difference goes in favor of the BSC students who we would conclude have a higher IQ overall. Right? One last thing to finish up the example, to interpret the p-value. The p-value means that if there was really no difference in the mean IQs of Samford and BSC students, we would get a test statistic like minus 3.226 or something more extreme than that, less than 1% of the time just due to chance. Right? In fact, it was about 0.19% of the time. That's really, really rare. So we're really, really sure that that beginning assumption of no difference was not a good assumption. Right? All right, so next up we'll do a confidence interval, then we'll do a StatCrunch example, and that'll do it for the term.